Visual survey is the physical assessment of a stream site. In this chapter, you'll learn how to characterize the environment through which your stream flows. This assessment helps to interpret water quality data and determine if there are observable problems in or around the stream. The visual survey is a detailed look at the physical characteristics of your stream site. We will cover characteristics of the floodplain, riparian zone, streambank, and streambed that influence the water quality of your stream. Finally, we will look at a few other ways to assess the health of your stream site. The purpose of visual survey is to record observations of the environment in and around the stream. These characteristics have a large effect on the water quality of your stream. By documenting conditions using visual survey, we can look at changes in the watershed and stream over time, which help get a better understanding of how water quality responds to those changes. Visual survey is conducted 2 times per year, once with the foliage present, around September or early October, once with the foliage absent, around February or March. These are also the times we recommend doing biological monitoring. This image is a hypothetical monitoring site in the area on which the visual survey should be conducted. Remember to always use the same 300-foot stretch at your stream site. Consistency in reporting is key because it allows us to capture changes over time. Here is the visual survey datasheet. This datasheet is subjective. If you monitor with a team, have the same person make the determination for the values for every monitoring trip. We will work through the sections, defining each physical parameter and explain exactly what to look for. As with all datasheets, the first section is the header information. This section is covered in the site selection chapter. This image is a cross-section of a stream site from bluff to bluff. It also shows a closer look from riparian zone to riparian zone. We will use this diagram to describe the different parts of the visual survey we are discussing. First, we will look at the floodplain. This is a flattened portion of the stream valley susceptible to flooding. The floodplain stretches from the riparian zone to the bluff on each side of the stream. In many streams, you will not be able to see the bluffs from the stream. On the visual survey datasheet, it lists options of land use, including industrial, commercial, residential, pasture hayfields, row crops, woods, or other. If you select other as a land use in your site's floodplain, be sure to specify or describe that land use. An example of other is city park or golf course. You will estimate the percentages of each land use. All percentages under floodplain land use should add up to 100%. Let's take a look at some examples of floodplain use. In this illustration of an unimpacted floodplain, land use has not negatively impacted water quality. The floodplain has a stair-stepped appearance due to normal intensity high water events. The riparian corridor is vegetated. Stream banks are gently sloping. Streambed is narrow with varying water depths. Here we have a photo of an unaltered or unimpacted floodplain of the Merrimack River. The floodplain is limited on one side by the bluff, so if it floods, the river will rise on one side opposite of the bluff. The floodplain is narrow and is in a natural state with the forest and grasses. This illustration shows a moderately impacted floodplain. Land use may affect the water quality of the stream, but the floodplain is still in good condition. The possibility of nutrient and sediment loading is increased by crop management practices and animal production activities. A vegetated riparian corridor mediates these threats to some extent by preventing erosion and taking up excess nutrients. The stream bank is moderately changed but has a gentle slope. The stream bed remains unaltered. This is a photo of a moderately impacted floodplain of the Thompson River near Trenton. Even with agricultural land use, this floodplain is in good condition because the riparian corridor is mostly intact. The vegetated riparian zone will slow water running over the land during precipitation events and prevent erosion. The vegetation will absorb nutrients and sediment before they enter the stream. The stream banks still have a gentle slope and the stream bed is unaltered. This illustration shows a heavily impacted floodplain. In this example, the floodplain contains land uses that have economic value and could be lost during a flood. Nutrients and sediment loading are a greater threat. permanent vegetation in riparian corridor is absent along with its benefits. Nutrients and sediment now directly enter the stream. Stream banks are steeper and more vertical due to the erosion or downcutting. They are vulnerable to severe erosion because there are no roots to stabilize the banks. Streambed is wider, shallower, and more uniform due to the sediment filling in the stream. This is a photo of a heavily impacted floodplain of Cane Creek Ditch in Neelyville. The stream has been channelized and the primary land use in the floodplain is row crops. Water flowing over the cropland will pick up excess nutrients and sediment. Since the riparian corridor is completely absent, these pollutants will directly enter the stream. The stream bed is wide and shallow, and the stream banks will be easily eroded if the stream floods. This illustration shows an urban development of a floodplain. Land uses include residential, roads, and other developments that will be threatened by flood events. The riparian corridor lacks vegetation. Stream banks are very steep and vertical. These banks will be prone to erosion. Stream bed is downcut and uniform. Downcutting is the process of erosion that causes deepening of the stream. All developments in this floodplain are at risk if there is a flood event. This photo of the Missouri River at Jefferson City shows mixed land use. This was taken before the flood of 1993. There is a bluff on the lower left side of the slide with railroad tracks at the base of the bluff. On the opposite side of the river, there was commercial, industrial, residential, and agricultural land use. The flood of 1993 damaged all of the land uses you see in this photo, and the floodplain now looks quite a bit different. The town of Cedar Hill in the upper right corner was completely inundated and has since been converted to parks and businesses that have to comply with floodplain regulations. Here we have another example of floodplain use. Just out of shot of the photo is a neighborhood to the right and a small cattle pasture to the left. For this site, land use includes commercial, residential, pasture hayfields, and woods. When filling out the datasheet, all these land uses must add up to 100%. Let's take a look at one more example of developments in a floodplain. This image is Fishpot Creek in St. Louis County. This shows what can happen when buildings are too close to a stream in a floodplain. Storm drains were redirected just upstream of this residential area. This resulted in higher flow through the section of stream and significant erosion of the stream banks. Here is the same section of stream on Fishpot Creek. The damage shown only took a few months to occur. Now that we have looked at floodplains, we will move into the riparian zone. The riparian zone, or riparian corridor, is a strip of land on each side of the stream. This starts from the top of the stream bank to 100 feet back from the stream on both sides of the stream. You will be evaluating the riparian zone for the full 300-foot monitoring site. The riparian cover is the different types of land use within the riparian zone of your stream site. You will estimate percentages of various types of riparian cover, including trees, grasses or weeds, bare ground, parking lots or streets, buildings, and other. If a value is entered under Other, describe the cover and enter the percentage. Total of percentage for riparian cover should equal 100%. This is a healthy riparian corridor along LaBarque Creek in Jefferson County. The riparian zone is in excellent condition with 100% trees and shrubs. Remember, the riparian corridor extends 100 feet away from the edge of the stream bank on both sides of the stream. This photo shows a highly altered riparian corridor along a stream in Howard County. There are only a few isolated trees along the stream reach. 99% of the corridor is overgrazed pasture. Note the eroding stream banks and the lack of any type of filter strip or vegetative buffer along the stream. This photo shows an urban stream in Jefferson City. Note the paved sidewalk, parking lot, and paved stream bed. Although there are a few trees along the stream, most of the riparian corridor is paved. We refer to this as impervious surfaces. There are also buildings in the riparian zone. Now that we have looked at the riparian zone, we will move in a little more to the stream bank. The stream bank is a portion of the stream area that rises from the stream bed and reaches a crest. If there is no noticeable crest and the slope of the stream bank is very gradual, consider the stream bank to extend no more than 50 feet from the edge of the stream bed. You will estimate percentages for stream bank conditions, including trees, grasses or weeds, bare ground, bedrock, pavement or riprap, and other. If a value is entered under Other, describe the conditions and enter a percentage. The total percentage for stream bank conditions should equal 100%. Here is an example of stable stream banks with trees and grasses along Blue Springs Creek. Vegetation covers the entire stream bank. There's no bare ground or eroding banks. This photo shows a stream bank along Lost Creek with bare ground and sparse trees. Trees were removed from the riparian corridor at this city park. This photo is the same park and same location as the previous photo. After 10 years, the stream is wider and the banks are eroded. The loss of vegetation in the riparian zone and stream banks has contributed to severe erosion of the stream banks. In this stream, riprap has been used to line the stream banks. Riprap is rocky material used to stabilize stream banks and protect against erosion. This is often used when a large portion of the watershed is covered with impervious surfaces, which causes fast, high-volume runoff. The size of the rock needed depends on how steep the stream banks are and the volume and velocity of water that the stream transports. As you can see from the trees collapsing into the stream, riprap may not solve all the stream's erosion problems. This is an urban stream with old pavement used as riprap. This is not an acceptable method of stream bank stabilization. Riprap must be engineered to fit the stream, and the appropriate material must be used so that it stays in place. As you can see, some of these concrete pieces have slid off the banks and the bare soil is exposed, which may increase erosion. Note the stormwater pipe at the edge of the stream. When this was routed to the stream, it would have been placed flush with the stream bank and stream bed. It is now sticking out about 4 feet into the stream, indicating much of the stream bed and banks have eroded since the pipe was placed. An alternative to riprap is paving the stream bed and stream banks, which is even worse for habitat. Impervious surfaces lack interstitial spaces needed for macroinvertebrates. This is called Detroit riprap. Vehicles were cabled together and then anchored to the stream bank. This used to be an acceptable way to control stream bank erosion in the 1950s throughout the U.S., but it is no longer used. This image of Grindstone Creek shows mixed bare ground and vegetated stream banks. It contains trees, grasses or weeds, and bare ground. Note the lack of riparian corridor and proximity of the road to the stream. Now we will look at the stream bed. This is the portion of the stream where water flows under normal conditions. You can usually tell a difference in substrate and vegetation between the stream bank and the stream bed. Gravel bars are considered to be part of the stream bed since they are covered by flowing water for at least part of the year. You will estimate percentages of stream bed composition within a riffle, including silt or mud, sand, gravel, cobble, boulder, and bedrock. Gravel is substrate that is larger than sand, but less than 2 inches in size. Cobble is substrate that is 2 to 10 inches. A boulder is substrate larger than 10 inches. If you do not have a riffle at your site, check the box for alternative habitat. The total percentages for stream bed composition should equal 100%. Let's take a look at the different types of stream bed substrates. Silt and mud are the smallest substrate. These fine sediments are smooth to the touch when you rub them between your fingers. In this photo of the Grand River, you can see that silt makes up a large percentage of the stream bed. Silt does not provide interstitial spaces needed for many aquatic organisms. This type of sediment is characteristic of streams in northern Missouri. The stream bed is 100% sand sediment. Sand will feel grainy and rough when you rub it between your fingers. The spaces between the sand particles are too small to provide habitat for most invertebrates and small fish. As a result, it does not support a wide variety of aquatic organisms. This stream bottom is primarily gravel with some sand. Gravel is defined as sediment larger than sand but less than 2 inches in size. This is a better substrate than sand for an invertebrate community. However, most of the interstitial spaces are filled with sand and there is little habitat for aquatic invertebrates. A large part of this stream bed is cobble, with some gravel and sand. Cobble ranges from 2 to 10 inches in size. It provides lots of interstitial spaces for aquatic invertebrates. This is the type of substrate that supports a diverse aquatic community. This stream bed is mostly composed of boulder substrate with some bedrock. Boulders are defined as any rock over 10 inches in diameter. Bedrock is large solid rock that lies beneath other substrate. There are still many places for macroinvertebrates to live, although the size of the boulders and the bedrock may limit some species. This stream bed is 100% bedrock. Bedrock resists erosion, but since it's usually smooth, it provides little habitat for aquatic invertebrates.
The last thing to look at within the stream bed is the percent embeddedness of cobble substrate. You'll pick up 5 cobble stones from the stream bed, ideally a riffle, and determine the average embeddedness from all 5 rocks. If there's no cobble at the stream site, just check the box on the datasheet that cobble substrate is not present.
Embeddedness can be determined by looking at the oxidation or algae on a rock. In this photo, you can see the algal growth above the embedded line. This cobble was about 30% embedded. This rock also has algae where the top was exposed. This was about 80% embedded. You would continue this evaluation for a total of 5 rocks. The datasheet provides easy instructions on how to calculate the average embeddedness. Here is an illustration to visualize embeddedness. Embeddedness refers to how much of the rock is embedded or buried in sand or silt. This is an indication of soil erosion. Greater embeddedness equals greater erosion or sedimentation. An embeddedness greater than 50% will negatively affect most pollution-sensitive species. Sedimentation contributes to impaired water quality in both rivers and lakes. Not only does sediment fill in interstitial spaces in the stream, but it also brings other contaminants into the water. High sediment loads can increase the turbidity or murkiness of the water, which influences water temperature and other chemical parameters. Best management practices has reduced sediment runoff rates from 5 tons per acre per year to about half a ton per acre per year. Both of the images show severe cases of sedimentation, both along Locust Creek. The top image is in Persing State Park. Channelization upstream of the site destabilized the stream and accelerated bank erosion. The bottom image at Fountain Grove Conservation Area shows a sedimentation around a sign that was once 4 feet off the ground. Let's look at some examples of embeddedness. A surface view of this substrate in Hinkson Creek shows low embeddedness and relatively clean cobble substrate with interstitial spaces for aquatic invertebrates. This substrate shows about 25% embeddedness from fine gravel. This cobble substrate has very high embeddedness from sand-sized particles. The next section of the datasheet is signs of human use. For your site, look around for any evidence of how people are using the area. Some examples include campfires, litter, fishing tackle, ATV tracks, horse trails, etc. In the image on the left at Rorke Creek, we can see ATV tracks, which are an obvious sign of human use. Sometimes you'll come across signs of human use that may need to be reported, like illegal dumping. In such a case, this dumping should be reported to the Missouri Department of Natural Resources Solid Waste Management Program. A sometimes less obvious sign of human use is gravel mining. Some gravel mining doesn't require a permit. Some gravel mining does require a permit. This photo is an example of how gravel mining should not be done. We can see gravel is piled up in the water and vehicles have driven in the stream bed. More information on sand and gravel mining can be found on the Department of Natural Resources website.
Next on the datasheet is looking at algae within the stream. First, estimate the percentage of the stream bottom that is covered with algae. You may have to walk up and down your 300-foot site to see where the algae is. Next, of the algae observed, enter the percentage of algae that is close-growing and the percentage that is filamentous. Close-growing algae is short in length and can sometimes look fuzzy. Filamentous algae is longer than 2 inches and can typically wave back and forth in flowing water. The sum of the percentage of close-growing and filamentous algae should equal 100%.
This photo shows close-growing algae on the larger substrate. Close-growing algae can be described as the rocks wearing a sweater because it usually looks like a fuzzy, soft covering on the rocks. It may appear to be uniform in color, often greenish-brown. In this photo of the Big Piney River, we can see filamentous algae. This was just downstream of a wastewater treatment plant where nutrients are high. Sometimes it's difficult to distinguish between algae and aquatic plants. Filamentous green algae consists of fine, green filaments that have no leaves, roots, stems, or flowers. It forms green, cottony masses that are free-floating or attached to rocks, debris, or other plants. Sometimes bubbles, generated by the plants or created by its decay, get trapped in the mats and make them buoyant. It grows practically any water that can support life and receives good light. As a general rule, if you don't see leaves, it's probably algae. If you can see leaves, it's an aquatic plant. Harmful algal blooms, or HABs, are becoming more prevalent, and we encourage volunteers to report them. They are usually caused by warm temperatures combined with a high nutrient load in a water body, and are formed by blue-green algae, or cyanobacteria, which can produce cyanotoxins. These toxins can cause illness and death in humans and animals. They often look like green or blue paint has been spilled on the surface of the water, or like pea soup. They are most common in lakes and ponds, but can also be found in streams, especially in slow-moving water or water that is pooled. If you are unsure whether or not a water body has a harmful algal bloom, remember, when in doubt, stay out. More information on HABs, including the reporting form, can be found on DNR's website. If you think you have found a harmful algal bloom, please report this concern. The easiest way to report a suspected HAB is to follow these instructions. This email goes to the HAB response team, and a member of this team may contact you for more information. It's a good idea to snap some photos of the algae at the site to send with the form.
Next on the datasheet are water color and water odor. It's easiest to evaluate these by scooping up some stream water in a clear container. Water can be a variety of colors. If there is algae in the water, it might be green. With high sediment load, it could be brown. It could even appear milky or have an oily sheen. In many streams, the water will have no odor. In others, it may smell musty, organic, or even smell like sewage. You might smell chemicals or oil. Circle the color and odor that best describes what you're seeing. If you circle other, describe what you saw in the comments at the bottom of the datasheet.
When you look at the water in the stream, it can appear to be the color of the stream bottom, which is misleading. Even though the water in the stream looks green, this is just the algae growing on the bottom, not the water itself. Scoop water in a clear plastic container to check the true color of the water. Using a container to smell your water will help you determine if the smell is the actual water or the environment around the stream.
The last section in the visual survey datasheet is weather conditions, specifically cloud cover. Please to know if the skies above your site at the time that you're sampling are clear, partly cloudy, or cloudy by circling one of the options available. Knowing these conditions can help us interpret other kinds of data that you collect at your site.
On all datasheets, there is a section for comments and fish present. In the comments section, add any observations you think might be important or of interest. Examples include lowest flow ever observed, or trees recently cleared from banks. If you observe dead fish or other evidence of a pollution event, it's fine to write it here, but please call the emergency numbers for the Environmental Emergency Response Hotline. Under Fish Present, simply check the yes or no box if you saw a fish at your site. We don't need to know the species or quantities. We just care to know that the stream supports aquatic vertebrates. Something else you may want to mention in the comment section is the observation of foam or iron oxidizing bacteria. Foam in the stream can be caused naturally by decomposition. To determine if it's natural, use the stick test. If the foam breaks apart when whacked with a stick, it's natural. If it doesn't break apart, it could be a detergent or another chemical. This would be a concern. It's somewhat common to see bright orange slime, often accompanied by what appears to be an oily sheen on the water. This is caused by naturally occurring iron oxidizing bacteria, which gets energy from the iron minerals leaching out of the soil. If you can break the sheen with a stick, it is organic and not a cause for concern. If you need guidance or definitions, more information can be found on the back of the datasheet. Additional resources and training videos can be found online. Contact us if you have any questions.